Okay, time for another deep dive.
Let's do it.
So today we're exploring kind of a neat intersection where calculus, maybe the stuff you're working through right now, actually meets something really practical.
Yeah, like keeping your food fresh.
Yeah,
Specifically, those sealed bags and containers, in the pantry.
exactly. We're digging into the source material you sent over, looking at how these, well, fundamental math principles are just key to understanding something that seems simple.
Right, like how oxygen actually gets into a sealed package.
Right.
Over time, obviously.
So our mission really is to unpack how differentiation and integration to these, core calculus ideas,
Uh-huh.
how they become tools, pretty powerful tools actually, for modeling that oxygen getting in.
And ultimately predicting shelf life,
Right.
which is the crucial bit for agro products.
Right. Let's see what the material tells us about how that connection works.
What was really fascinating, I think, is seeing calculus move from, abstract ideas to a very direct engineering thing.
Okay.
You might think of differentiation maybe as finding the instantaneous rate.
Right.
Like, how fast is oxygen sneaking in right now at this very second?
Ah, okay. Like a speed.
Sort of, yeah.
Yeah.
The sources show this relates directly to the flux of oxygen molecules crossing that packaging barrier.
Flux. Okay, so not just a vague rate then, but a specific measure, like flow.
Exactly, a measure of flow.
Yeah.
And then integration.
Mm-hmm.
So that's where you figure out the total, right?
Total amount that's managed to get inside the package.
That's it. Yeah, integration basically sums up all those tiny instantaneous fluxes over a period of time.
Okay.
And the sources really emphasize that this cumulative amount of oxygen, the total that's gotten in, that's the critical thing.
Right, because it's not just the speed at one moment.
No, it's the total volume that's built up inside since it was sealed.
Okay, that makes total sense, because that cumulative amount is what actually reacts with the food, right?
Yeah.
Causes it to spoil and degrade.
Precisely. So the math is directly modeling the very process leading to spoilage. And the sources, they explain how different things affect that rate, like the packaging material itself.
Like how thick it is, or what it's made of.
Exactly. Its thickness, its permeability coefficient, basically how easily oxygen gets through it. Temperature changes things too, even the initial pressure difference between inside and outside.
Wow, okay. Lots of variables.
Yep. And they all influence that diffusion rate, the dxdt, if you want to think of it that way.
Okay.
Calculus gives you the framework to build models that actually account for all these things.
So is that where simulation comes in? You use differentiation to sort of describe the rate with all those factors, and then you integrate over time to like simulate what the oxygen level will be.
That's a really good way to put it, actually. The simulation, essentially, it solves these differential equations. It integrates that rate of oxygen entry over, days, weeks, months.
Right.
And that lets engineers predict when the oxygen concentration inside is going to hit some critical level.
A level that means the food isn't good anymore.
Yeah, a threshold where quality or maybe even safety is compromised.
Okay, and here's where it gets really interesting for you listening in. This isn't just, theory for academics.
Not at all.
This modeling, this calculus differentiation integration, it's literally shaping how packaging is designed.
Yeah.
And it's setting those expiry dates on the food you actually buy.
Absolutely. Every decision, like what type of plastic to use or how many layers in the film, it involves understanding these diffusion dynamics, and calculus is the tool for that.
It really shows how these math concepts you encounter, they aren't just stuff in textbooks.
They're quantitative tools,
Oh.
powerful ones, used every day in industries like food science, packaging, engineering.
Solving real problems.
Yeah, solving real-world problems, like cutting down on food waste, making sure products are good quality on a huge scale.
It's pretty amazing seeing that link so clearly. Differentiation tells you the speed the oxygen's getting in.
At any moment.
And integration adds it all up, the total distance traveled, if you like, the total oxygen inside.
And that total is basically the countdown clock for shelf life.
Yeah.
So I think the main takeaway here is pretty clear. Getting a handle on the mathematical tools to describe rates of change and accumulation. It's just fundamental.
Crucial.
Yeah, crucial for predicting really important outcomes in the physical world.
Yeah.
From designing packaging to just understanding how long stuff stays viable.
So next time you're looking at a calculus problem, maybe, or honestly just checking the best before date on your crisps. Think about the math that probably went into that date.
Which kind of leads us to a final thought for you to chew on.
Okay.
Beyond food packaging,
Sure.
where else might these calculus concepts, the ones you're learning, show up in like surprising practical ways all around you?
Good question.
Yeah. Start looking for those rates, those accumulations.
Hmm.
They're often hidden in plain sight.